So, hello everyone again. This is lecture 1 part 3 of Semiconductor Electronics, Materials, Devices and Simple Circuits. In the previous two parts we completed the introduction part of this lecture. Right now we are on the classification of metals, semiconductors and insulators. Let us try to understand. In the previous part we have understood on the basis of your conductivity. In this part we will go on with further discussions on the basis of energy bands. We will try to understand what are these energy bands and then move on with the further discussions. So, I am Sameer Lavankar, let us begin our discussion. Okay. So, right now the introduction part of this lecture is completed. We understood the difference between the vacuum tubes or valves and the basic today's semiconductor devices. What were the drawbacks of the vacuum tubes, what were the sizes of the vacuum tubes, what was the voltage required for the vacuum tubes to work, etc., as compared to the today's semiconductor devices. Right now let us move on with further discussions on classification of metals, conductors and semiconductors. Okay. Okay. So, in the last part we understood that yes, so there is isolated atom, and then there is atoms in a solid. So, these isolated atoms have a very large space for it to work, but what happens is when the atoms clump close together to form a solid and they are very close to each other, then what happens is that the nature of electron motion in a solid is very different from that in an isolated atom. Inside the crystal, each electron has a unique position and no two electrons can see exactly the same pattern of surrounding charges. Why? Because let us say this is one of the atom, this is one of the atom, these are all the atoms. Let us say I am not making the orbits for now. Let us say this is how the atoms are being put apart. Okay. So, let us say the electrons would be residing somewhere here. Let us say I am not making the lines for now, I am just making the electrons. So, electrons are different for different. Okay. So, what they are just trying to say that the amount of charges which this electron would have from the surrounding charges will be different from the amount of electrons or the amount of charges which this electron will have. Let us say this is the electron 1, this is electron 2. So, this has only been explained in this line in this line that inside the crystal each electron has a unique position, quite evident, as you can see that it is having a unique position, and no two electrons see exactly the same pattern of surrounding charges. Because of this, each electron will have a different energy level, as in what does it mean by energy level? That the amount of energy which it has, there will be some attraction, there will be some repulsion. Due to that, the amount of energy that the electron have is different for different electrons. Why it is different? One of the reason is that it has a unique position, and another is that no two electrons see exactly the same pattern of surrounding charges. That is why each electron will have different energy level. Different energy level as in it is having different amount of energies. Okay. These different energy levels with continuous energy variation, quite evident, these atoms can collide with each other, they can change its positions also. Due to that, the amount of charges can also change, and therefore there is variation in this energy level also. So, these different energy levels with continuous energy variation form what are called as energy bands. Okay. So, these are nothing but called as energy bands. I made you understood that what is basically the crux behind the concept of energy bands and basically what is the definition of your energy bands. Okay. The energy band which includes the energy levels of the valence electron is called the valence band. Okay. So, this is your valence band, this is your conduction band. Okay. The energy band, the different energy levels with continuous energy variation form what are called energy bands. The energy band which includes the energy levels of the valence electrons. In your chemistry you may have heard what are valence electrons. The electrons which are residing on the outermost orbit of an atom are called as valence electrons. So, basically the variation in the position of the valence electrons and the variation in the energy of the valence electrons due to the difference in the position of the surrounding charges or the amount of energy which the surrounding charges are giving to the valence electrons leads to the formation of the valence bands. Okay. So the energy band which includes the energy levels of the valence electrons is called the valence band. The energy band above the valence band is called the conduction band. What is the application of conduction band will be explained. For now you can just understand that there is something called as valence band, above it is something called as conduction band. As the name suggests, sorry, not the name suggesting, as the energy, as you can just refer to this, that the energy of the conduction band is higher than this valence band. Okay. So this thing has also been explained. So in this lecture, in this slide, we understood basically what is valence bands, what is energy band, what is conduction band, etc. Okay. With no external energy, all the valence electrons will reside in the valence band. Quite evident, because there is no input of energy is being put into the valence electrons. Okay. In the chemistry classes, you may have heard that if the sufficient amount of energy is being imparted into the electrons, let us say valence electrons, then the electrons get excited up and can go on to the further higher orbits. Same concept can be applied here also. How we are trying to apply? We are trying to apply the concepts in terms of excitation of these valence electrons, as the name suggests, valence electrons. So those electrons will be present in the valence bands. Where it will get excited? It will get excited into the conduction band. The concept of formation, the concept of excitation of valence electrons from its orbit into the higher orbit in chemistry is being analogous to the excitation of valence bands, excitation of valence electrons from the valence bands into the conduction band. This is how it can be understood. Okay. So with no external energy, all the valence electrons will reside in the valence band. Very quite evident. If the lowest level in the conduction band happens to be lower than the highest level of the valence band, the electrons from the valence band can easily move into the conduction band. For this line, just refer to this location here. Okay. So what does it try to say? Let us say that this conduction band, the lowest level, let us say this is the lowest level. Let me change the color for more clarity. Let us say this is the lowest level. Okay, this color is not visible. Okay. Let us say this is the lowest level of your conduction band, and let us say that this is the highest level of your valence band. So basically what we are trying to understand is that there is some mixing of your valence band and conduction band. Okay. So let us reiterate the statement again. So if the lowest level in the conduction band, happens to be lower than the highest level of the valence band, the electrons from the valence band can easily move into the conduction band. Quite evident, because these valence band can reside anywhere here, and these conduction band, as the conduction band is present till this point, so these can directly reside from valence band to conduction band. Okay. Normally the conduction band is empty. Okay, so till now was to one point. Now they are trying to make understand some another assumption. Normally the conduction band is empty, but when it overlaps on the valence band, electrons can move freely into it. Quite evident, electrons can move freely into it because there is no energy gap. This is the case with metallic conductors. So this is how we can classify the metallic conductors. Okay. So basically generally if we can make the diagrams of energy, so basically these diagrams which I just made, so these diagrams are nothing but called as energy band diagrams. So if we try to make energy band diagrams for metals, then generally or very generally, not every time for metals, because they are conductors of electricity, the conduction band and the valence band are colliding with each other, as in they are superimposing each other, partly they are superimposing each other. Okay. So this is the case of metallic conductors. Okay. Now if there is some gap between the conduction band and the valence band, let us look over to this figure now. So if there is some gap between the conduction band and the valence band, electrons in the valence band all remain bound and no free electrons are available in the conduction band, because there is a forbidden region, there is an energy gap presenting here. As you can see, there is a gap here. This gap is nothing but called as energy gap. So because of this gap being present, the electrons in the valence band cannot excite it to the conduction band. This makes the material an insulator. So, normally all the insulators have this forbidden region, or let us say have this energy gap. You can refer to the energy gap also, that this energy gap is greater than 5 electron volts. Okay. Moving on, but some of the electrons from the valence band may gain external energy to cross the gap between the conduction band and the valence band. Then these electrons will move into the conduction band. At the same time, they will create vacant energy levels in the valence band where other valence electrons can move. Thus, the process creates the possibility of conduction due to electrons in conduction band as well as vacancies due to valence band. What they are trying to make you understand is, they are just trying to say, let us say, I will make it much more clear everything which is written here. Let us say I am denoting the electrons by this red circles. Okay, these are the electrons. As the conduction band is empty, there would be some places vacant here. What would be added in these places? The electrons will be added in these places. Let us say by some means or necessary. Okay, let us try to make this, because in insulator generally this won't work. In valence, in semiconductors it would work. So I will try to make you understand this concept in semiconductors only, so as to avoid confusion. Okay, so let us say in the valence band you have electrons, and in the conduction band you have the empty spaces. Okay, so basically what would happen is, let us say by some means or necessary we try to impart energy into it, and let us say that energy was approximately 1 electron volts or greater than 1 electron volts, and what would happen, this electron would get excited up and can fill up this space. So if this space is filled, that means there is a hole created at this location. Similarly, let us say we excite this and this is being added up here, then this hole would be filled up and this would create a hole here. This is only been explained in the slides here. Okay. So what is written? But some of the electrons from the valence band may gain external energy. Let us say I impart some external energy into it. To cross the gap between the conduction band and the valence band. So to cross the gap, so this is that gap being talked about. So I am imparting an external energy to cross this gap. Then these electrons will move into the conduction band. As you can see, these electrons will move into the conduction band. At the same time, they will create vacant energy levels in the valence band. You can see that the vacant energy levels are being created here. Okay, where other valence electrons can move. So basically what would happen is, these valence electrons can even move into these holes. So what would have happened then? Let us say if these are moving here, then there will be vacant spaces available here and the electrons will be filled here. Okay, so this is basically what is being explained in these 3 lines. So I basically explained to you using the diagrams. Okay. Thus, the process creates the possibility of conduction due to electrons in the conduction band as well as due to vacancies in the valence band. So, what does it try to say? Please remember, please look over to the last line very carefully. Okay, the last line is trying to make you understand that the conduction will appear when there is a flow of electrons. The flow of electrons here are in 2 ways. One way is, I will write so that it is much more clearer. Okay, so one way is movement of electrons from valence band to conduction band, and second is movement of electrons, this will be inside valence band due to empty spaces created by the movement in 1. Okay, so because of movement of electrons from, let's say, valence band to the conduction band, and second is because of this movement there is a hole being created here, and because if there is a hole being created here, some another electrons in the valence band can move from this, let us say, this location into this location. So hence there is a movement there also, and hence if there is a movement, there is a chance, there is a very high chance that there is a conduction possibility. So that has only been explained in the last line. Thus, the process creates the possibility of conduction due to electrons in the conduction band, and here also there are some empty space, there are some electrons, so there can be movement in the conduction band also. So that can be third possibility, as well as due to vacancy in the valence band, because there are vacancies here also being formed, so there can be conduction. So basically this can be related to the movement inside conduction band. Conduction band. Okay, so major possibility conduction is electrons in conduction band. So due to this, so this this can be said as this is the first part. The reason is only this. So this can be said as movement is possibility of conduction due to electrons in conduction band, and second is due to vacancies in the valence band. So this is how the conduction has been explained here. Okay, let's move on. So let us consider what happens in the case of silicon or germanium crystal containing N atoms. Okay, so now we will go into some of the chemistry regarding this. So a little bit detailing of your Bohr's atomic model will be used here. I will go very slowly so as to make you understand whatever is written here. For now, let's not look over to the figures written here, because this may be a little difficult to understand. I will make you understand everything which is written in this picture. For now, just look over to the things written on the left. Okay. So let us consider what happens in the case of silicon or germanium crystals containing N atoms. Okay. For silicon, the outermost orbit is the third orbit, while for germanium it is the fourth orbit. So these are the basic chemistry detailing only. So I won't go into that detail now. So this is known to us. This is known to us. So for silicon, the outermost orbit is the third orbit, while for germanium it is the fourth orbit. The number of electrons in the outermost orbit is 4, 2s and 2p electrons. Okay. Hence, the number of outer electrons in the crystal is 4n, as there are number of atoms are n, therefore this is 4n. Okay, these are all the chemistry concepts. That is why I am not going into the detailing of how they came. The maximum possible number of electrons in the outer orbit is 8. How it is 8? So there are 2 s electrons and 6 p electrons. So therefore, the number of electrons in outer orbit is 4, but the maximum possible number of electrons in outer orbit is 8. Okay, therefore the 4n valence electrons, there are 4n valence electrons, there is 4 multiplied by n, and there are 8n available energy states. So this is how we can understand that how the movement of electrons can be occurring in different energy states. Okay, let's stop the discussion here only for this lecture. I will try to make you understand much more detailing about this in the subsequent classes. Very interesting, this complete chemistry is also very interesting. We will try to understand what is happening, how are the states being formed, why is the state being called as this state only, what are these regions being explained. This is also one of the peculiar topics which I need to make you understand. Okay, so we will go bit by bit with everything. For now, let me stop the lecture here only. So in this lecture we understood basically what are energy bands and how are the classification of conductors in semiconductors and insulators being done on the topic or on the basis of on the basis of energy bands. We understood about energy bands, we understood about valence band, we understood about this conduction band, etc. in this lecture. Initially we started with the introduction of this chemistry behind the energy states, valence electrons and available energy states. I may revise this in the next lecture and then we can move further. Okay, so let me stop it here only. Thank you so much for this lecture.